Namaste. In the previous class, we got introduced to the various chemical properties of alkenes. Specifically, we were interested in addition reactions. And under addition reactions, we came across a rule called as Markovnikov's rule. The Markovnikov's rule is applicable for unsymmetrical alkenes when they add on to an unsymmetrical molecule. So we looked at how Markovnikov's rule plays a role in defining who is the major product and the minor product in a series of examples. We also looked at one more rule called as anti-Markovnikov's rule, which is also called as Karash effect. And it is applicable only when there is HBr in the presence of a peroxide. So this is what we studied in the previous class. And we told you that this is one of the most important rules that's applicable in unsaturated compounds when we talk about addition. We'll continue further. We will try to complete the last part of alkenes today in this class. We'll continue with the next set of properties. The next chemical property is addition of sulfuric acid. So we know sulfuric acid. Sulfuric acid has the formula H2SO4. So how does sulfuric acid add on to an alkene? So cold concentrated sulfuric acids add to alkenes in accordance to Markovnikov's rule. So this addition is also happening via Markovnikov's rule to form alkyl hydrogen sulfate by electrophilic addition reaction. This is step one. So let's try to see how it actually happens. If I take an ethene, I add sulfuric acid. Here it is just written in a different way to just make you understand who is attacking. Under cold conditions, H plus will attack one of the carbon atoms of the double bond. HSO4 minus will attack the other carbon involved in the double bond, giving us this molecule, which is called ethyl hydrogen sulfate. What happens in the second step, depending upon the bulkiness of the group that's around, we can either have elimination reaction happening or the product will remain as ethyl hydrogen sulfate. Yeah, so this is one of the ways in which sulfuric acid adds on to an alkene. And we saw this with respect to a symmetrical alkene. If we start with an unsymmetrical alkene, you know that we need to follow Markovnikov's rule. If we start with an unsymmetrical alkene, the positive part will attack the carbon of the double bond having more number of hydrogens, and the negative part will attack the carbon having lesser number of hydrogens. Depending upon that, you will arrive at a hydrogen sulfate in two different forms. One will be the major product and the other will be the minor product. So that is something that you would have clearly understood based on Markovnikov's rule. We look at addition of water in the second step. In the presence of few drops of concentrated sulfuric acid, alkenes react with water to form alcohols in according to Markovnikov's rule. So what happens is you have this ethyl hydrogen sulfate that's obtained in the previous step. It reacts with water. When it reacts with water and we boil, H will take away HSO4 minus as H2SO4. So HSO4 goes out, gets eliminated as H2SO4 upon combination with H plus. And in place of HSO4 minus, who gets substituted, I will have OH getting substituted. This is step two, and this will be your final product, which is an alcohol. So in step one, what did we see? We looked at addition of H2SO4. According to Markovnikov's rule, if at all, I start with an unsymmetrical alkene, giving me an ethyl hydrogen sulfate. Then in the second step, there is addition of water. We will have H plus taking away HSO4 minus to go out as H2SO4. And in place of HSO4 minus, we have OH minus coming in to form an alcohol. So if you take an alkene, react it with sulfuric acid in the presence of water, the final product is an alcohol. So this is what you need to remember. So this is an example of an unsymmetrical alkene. So in the previous case, we looked at ethene, which was symmetrical. In this case, it's an unsymmetrical alkene. So you would know that Markovnikov's rule will be applicable here. So who will add on where? H plus will add where? OH minus will add where? From water. Yeah. So if you follow Markovnikov's rule, H plus will add to CH2 and OH minus will add to CH, giving us this compound, which is propan 2-ol, which will be the major product. Okay. So we will also get the minor product, which is the Markovnikov minor product. Markovnikov minor product will be propan 1-ol. So this is basically the overall reaction when an alkene is made to react with water in the presence of sulfuric acid. Let's try to solve a few MCQs here. Reagent used in hydration of alkenes. Reagent used in hydration of alkenes is sulfuric acid, Hg2 plus in H2SO4, aqueous KOH, or whether it is none of these. Reagent used in the hydration of alkenes. Now, as the name itself indicates, it is a hydration. Hydration means addition of water. Now, which of these reagents is used for the addition of water? We just saw it. It is aqueous H2SO4, water in the presence of sulfuric acid or sulfuric acid dissolved in water. That will carry out hydration of an alkene to give us what as a product? Yes, alcohols as the product. Let's look at the next set of chemical properties. Oxidation. Now, by now, we are very familiar with what oxidation is all about. Oxidation is addition of oxygen. Oxidation is removal of hydrogen, or oxidation is loss of electrons. So these are the three definitions, standard definitions for oxidation. So let's try to see what's happening in the case of alkenes here. When alkenes react with hot acidified KMnO4, we get carboxylic acid as the product. So when an alkene is made to react with acidified potassium permanganate, KMnO4, which is a strong oxidizing agent, strong oxidation takes place to give us carboxylic acid. Let's have a look at the example. So this is 2-methyl-butene. So 2-methyl-butene. This is your starting compound. This is made to react with KMnO4 in the presence of heat. So what do you think will happen? The bond will break across the double bond. So there is a break across the double bond, giving us CH3, COCH3. So one of the oxygens get added to this part of the breakage, giving us CH3, COCH3, and the other oxygen gets added to the other part of the breakage to form CH3, CHO. We get aldehyde. So these are aldehyde and ketones. Acetaldehyde is one of the products, and acetone is the other product. Now you need to clearly understand the type of product is entirely dependent upon the starting compound. All you need to do is break the double bond and then add oxygen atoms across the break, giving you two different compounds. Now this, upon further oxidation, will give us acetic acid. So whatever aldehyde is obtained in presence of KMnO4 will undergo oxidation to give a carboxylic acid. So that is what is mentioned in this example here. So end result is the formation of a carboxylic acid. Now, why are we getting a carboxylic acid? Because we are starting with a strong oxidizing agent. A strong oxidizing agent will convert an aldehyde into a carboxylic acid. That's what is seen in this case when This compound 2-methylbutene is made to undergo oxidation in the presence of caminophore and heat. We initially get a mixture of an aldehyde and a ketone, and the aldehyde will further get oxidized. The ketone will also get further oxidized to give us carboxylic acids. When alkenes react with cold dilute and alkaline caminophore, which is called as Bayer's reagent, very, very important. So there's a reagent which has a name, which is called as Bayer's reagent. So what is Bayer's reagent? Cold dilute and alkaline caminophore. Yeah. So when we react alkenes with this, the product is not a carboxylic acid, but the product is a diol. Now, diol, as the name itself indicates, there'll be two OH groups. Ol is a suffix used for an alcohol. An alcohol is indicated by an OH group. So a diol is a compound that contains two OH groups. So let's take an example to understand this. This is 2-butene. When 2-butene is made to react with water and nascent oxygen, which is given by caminophore, which is given by Bayer's reagent, what do we get? Just like the previous case, we will have a bond being broken and two OH groups getting added across the break. So a bond breaks out of the double bond. Whichever is the easier bond to break will break. And which is that? Yes, it's a pi bond. The pi bond will break, and then both the OH groups will get added to the respective carbon atoms, giving us a diol, so which is butane 2,3-diol in this case. The next important reaction is called as ozonolysis reaction. So the next reaction is called as ozonolysis reaction. Now let's try to understand what is there in the name of the reaction. It is called ozonolysis reaction. Now it is clearly understood that I can break this compound into two, or break this word into two different parts: ozone and lysis. Lysis is break, and ozone is nothing but O3. So which means this reaction involves ozone, and this reaction also involves some break. Hence this reaction is called as ozonolysis reaction. So let's try to understand it in simple terms. Ozonolysis is nothing but addition of ozone molecules to alkenes first to form an ozonide. So ozone molecule will add to the alkene to first form what? To first form an ozonide. And then cleavage of the ozonide. Cleavage here indicates lysis. Lysis of the ozonide by zinc water to form smaller molecules. This reaction is what is called as ozonolysis. So if I have to put it in very simple words, ozonolysis basically involves addition of ozone molecule to an alkene and then subsequent lysis of that ozonide to give us smaller products in the presence of zinc and water. We'll understand this clearly when we take an example. So this reaction is basically used to locate the position and find the number of double bonds present in an alkene. So why is this reaction useful? If you want to know where is the double bond, whether it's in the second position, first position, 8th position, 20th position, if you want to know where is the position of the double bond, you use this reaction. And also to find out the number of double bonds, whether I have one, whether I have two, whether I have three, whether I have 10 double bonds in the given molecule. So how does that happen? Pretty straightforward. Ozone will add across the double bond. So wherever there is a double bond, ozone will go and add across the double bond to form the ozonide. Then what happens? There is lysis to form smaller molecules. So ozone is like a magnet. It gets attracted towards a double bond. Clear? we'll understand this better when we take an example. So this is ethene. When ethene is made to react with ozone in the presence of carbon tetrachloride, there is addition of ozone to form the ozonide. Now, how does that happen? You can see that the bonds are broken. The bonds which form the double bond are broken, and then the ozone molecule adds between the carbon atoms which had the double bond, like this. Got that? So you can clearly see from ethene to this ozonide, what has happened? The bonds between the carbon and carbon, not just the pi bond, but the sigma bond too. Both the bonds are broken, and then bonds are formed between carbons and the oxygens of the ozone to give us ozonide. So this is what is called as a ozonide. And then what did we understand? From the ozonide, in the presence of zinc and water, there is cleavage, there is lysis. This is the first breakage, what is indicated in red. When this break happens, whatever is the small portion that is there on the left-hand side of that break, HCHO, formaldehyde is formed. There's one more breakage. When this breakage happens, this portion will also give me formaldehyde, HCHO. And then what is remaining there? I have oxygen. Oxygen will go out as ZNO. So this should be pretty straightforward for you to understand. All you need to know is whenever there is a double bond, the ozone will add across the double bond. Now, how will it add? The bond between carbon and carbon. And when I say bond, it is bonds. Both the pi bond as well as sigma bond are broken. And once that happens, the ozone molecule will add across the carbon and carbon atoms which had the double bond to form an ozonide. Now, once the ozonide is formed in the presence of zinc and water, it breaks at two places. It breaks to give us multiple parts. To be more specific, it breaks into give 3 parts. Depending upon what is the composition, you get the respective compound, respective products. In this case, the components formed formaldehyde, and the last component, which is oxygen, is removed as zinc oxide. So this is pretty straightforward. If you understand this example, anyone gives you any alkene, you can just apply the same logic here. But depending upon what are the substituents, you will get different byproducts. Okay, so this is ozonolysis reaction. Let's take one more example. I want you to do this right now. So I'll give you, say, 5 minutes. Take this example, write it in your book, and then carry out ozonolysis. Okay, carry out ozonolysis. Add ozone. So I've already told you, first step is addition of ozone to form the ozonide. Once the ozonide is formed, then it reacts with zinc and water to form the respective byproducts. So make a note of this starting compound. Have you made a note of it? If you have made a note of it, I will show the previous slide for your reference. So this is the previous reaction that we studied. Using this, I want you to complete the reaction for propene. Done? Done? All right. So what did I give you? I gave you propene. Propene was made to react with ozone in the presence of carbon tetrachloride. That gives us the ozonide. And then from the ozonide, there is lysis using zinc and water. The first lysis or the first break will give you acetaldehyde. In the previous case, you got formaldehyde because you did not have CH3 as one of the groups, whereas here CH3 is one of the groups, one of the substituents. So therefore, I get acetaldehyde. And the second one will be formaldehyde plus zinc oxide. So this is ozonolysis of propene. I want you to take the next question as homework. 2-butene. Start from 2-butene. From 2-butene, find out the product of ozonolysis. So starting from 2-butene, find out the products of ozonolysis. Okay, so pretty straightforward. If you have understood this one and the previous example, finding out the products for 2-butene will not be so difficult. So apply the same logic, carry out the lysis, and then you will get the products. All right, let's solve a few questions. An alkene on ozonolysis produces a mixture of acetaldehyde and acetone. Identify the alkene. So I want you to do this right now. So take this question. He says an alkene on ozonolysis produces a mixture of acetaldehyde and acetone. So you should get acetaldehyde as one of the products and acetone as the other product. Identify the alkene. Now, what is acetaldehyde? You studied this in the previous example. Acetaldehyde is CH3CHO. What is acetone? Acetone, as the name itself indicates, it's a ketone. Acetone is CH3COCH3. What is acetone? CH3COCH3. So you need to get these two as the products. If these two are the products, what is the starting alkene is the question. So now you can clearly understand in the previous 3 examples, we started with an alkene and you were asked to find out the end products. But in this question, they've given you the end products. From the end products, you need to go back and identify the starting alkene. So go ahead, do it. So if you want a reference, I will show this slide so that you have a reference reaction. Now in this reaction, there's already one product, acetaldehyde is already there. You need to add one more product, which is acetone, and then go ahead in the reverse direction to find out who is the starting compound. This will really test your understanding. This is what is called as application-based questions, where you are applying whatever you studied. A PU question will be like this. Write the ozonolysis reaction for ethene. Write ozonolysis reaction for propene. That will be your PU question. But whatever question is given to you right now is a competitive question where you are supposed to apply the knowledge that you studied from PU. Go ahead, write the starting compound. Okay, so with this reference, I'll again go back to the question. The 4 options. Is the starting compound butanene? Is it butene? Is it 2-methyl butanene or 2-methyl butene? I hope a few of you would have got the answer for this. If you are struggling, don't worry. We'll just look at the solution and we'll be able to understand where we are stuck so that it's easier for us to understand the next time when we do something like this. So what is happening is the alkene, upon reaction with ozone in carbon tetrachloride and zinc and water, gives us two products. Which are the two products? First one is acetaldehyde, which is CH3COCH3, and the second one is acetone, which is CH3COCH3. In fact, finding an answer for this question does not require you to write down the entire steps. You need not follow writing all the 2 steps. All you need to do is remove both the oxygen atoms and join the carbon atoms by the double bond. That's all. So remove both the oxygen atoms, oxygen from acetaldehyde and oxygen from acetone, then combine these 2 parts. You get an alkene. That is your starting alkene. Simple. So that's what I've done here. I've removed both the oxygens and brought them together to give you an alkene. This is your starting alkene. And what's the name of this? Yes, it is 2-methyl butene. 2-methyl butene. So very simple way of identifying the alkene. Yeah, that's the shortcut. Write the structures of the final products that is mentioned in the question. Remove the oxygens, bring the carbons together and form a double bond. That is your starting alkene. Easy, isn't it? Yeah, so 2-methyl butene is your answer. Bayer's reagent is, we just saw it. Bayer's reagent is what? Is it acidified KMnO4 in heat, or acidified potassium dichromate? Is it cold alkaline KMnO4, or is it FeSO4 in the presence of a peroxide? Which of these reagents is Bayer's reagent? Yes, it is cold alkaline KMnO4. Coming to the last part of the properties, polymerization of ethene. So polymerization, if I look at that word, poly means many, mer means unit. So many units to form a polymer. Clear? So polymerization is a process of getting a polymer starting from a monomer. A monomer is a single unit. You combine n number of single units to form a polymer, which has many number of those units. That's what is called as a polymer. So if I start with ethene, it will undergo polymerization to give what is we are going to study now. A process in which a large number of small molecules combine together to form a long chain molecule, which is called as a polymer, is called as polymerization. A polymer is a macromolecule. Macromolecule means it's a big molecule consisting of a large number of repeating units known as monomers. Mono means one, mer means unit. So I will have a large number of repeating units called as monomers joined together to form a long chain called as a polymer. Poly means many, mer means unit. So let's understand how polymerization happens in ethene. Ethene at a very high temperature in the presence of oxygen and pressure. So you need high temperature, pressure, and oxygen. Ethene, N molecules of ethene will give us a long chain which is indicated like this. Yeah. So you see the brackets there. Inside the brackets, I have CH2 single bond CH2. And this is the unit that repeats n number of times to form a long chain. This polymer is called as polyethene. So you should be very, very familiar with this. Your polyethene covers, or nothing but your plastic covers, is actually polyethene. And in our regular language, polyethene has become polythene. So remember your roadside vendor or your provision shop owner, or remember yourself or your parents. One polythene cover kodi, give me a polythene cover. So polythene is actually polyethene. Yeah, so polyethene is a polymer that is formed when N molecules of ethene combine to form a long chain compound in the presence of oxygen, high temperature, and pressure. So this brings us to the last part of our understanding. Why do we need to study these compounds? Why do we need to study alkenes? Now, some of you have been asking me, some of you have not asked me, but it is there in your mind and your thought process. Why do I need to study all this? What is the use of all these reactions? Trust me, you will understand only when you see where it is used, where is it commercially important. For example, the previous reaction that we studied, the formation of polyethene. So can you imagine your life without plastics today? You cannot. Everything around you has something that is associated with plastic. Formation of plastic is a polymerization reaction and one of the most important chemical reactions out there. So like that, there are a lot of compounds that are very useful to man, and that's what we will try to understand under uses. Ethene is used in oxyethylene flame, which is used for cutting and welding of metal. Now, have you visited these fabrication shops where they cut metal and they weld metal? You see that flame that they use, usually the bluish yellow flame. That flame is actually from ethene. So ethene is used in oxyethylene flame, which is used for cutting and welding metal. Yeah, this is what it is. Ethene is used in preparation of ethylene glycol, which is used as an antifreeze agent. So ethylene glycol is an antifreeze agent in automobiles as coolant. Ethylene is used in the preparation of organic compounds like ethyl alcohol, acetaldehyde, acetic acid, etc., which are starting compounds for various other reactions and are used as solvents. Ethene is also used to manufacture polythene, which is used to prepare pipes, bottles, bags, etc. So these are the various products that can actually be prepared from polyethene. Yeah, your bottles, your covers, your bags, all of this is polyethene. Probably this itself is more than enough to understand the importance of alkenes. Ethene is used for artificial ripening of fruits. Now, you would have heard about this artificial ripening. Fruits, if they have to be left for natural ripening, will take its own time. But nowadays, people are not patient enough. They want everything quickly, and they want fruits also to ripen quickly. And how do they do that? By using ethene for artificial ripening. Ethene is also used as an anesthetic. Now, who is an anesthetic? And what is an anesthetic? Anesthetic is nothing but an anesthesia. Now, where is anesthesia given? You would have already come across that. Yeah. So whenever you visit a dentist, your dentist will give an injection before performing some surgery or some operation to your tooth. And before doing that, he gives you an injection, which is called as an anesthesia. So an anesthesia is something which will enable you not to experience pain. Yeah, it will numb that particular portion wherever the injection was given. You will experience zero pain. Yeah, which is very important, right? So it's used also as an anesthetic. Ethane is used in the preparation of mustard gas, which is also called as war gas. Yeah, so this is the formula of mustard gas. It's also called as war gas. So take a homework. I want you to find out where was this mustard gas used, or where is this mustard gas used? Why is it called as war gas? Find out where is mustard gas used. Let's solve a few MCQs. Phenomenon of adding of simple molecules like monomers to form big or giant molecule is called as ozonolysis, hydrogenation, polymerization, or oxidation. What is it? Yes, we just spoke about it, which is polymerization. So that's it for alkenes. In the next class, we will start from alkynes. We have already seen what alkynes are, how to name them. We'll continue with the preparation of alkynes, and we will go to the chemical properties and physical properties of alkynes. So that's the last part of hydrocarbons. And once we finish that, we will go to aromatic compounds, study of benzene and its compounds. So until the next class, namaste. Thank you.